Okay, good evening everybody. So today we're going to talk about chapter 11, vectors. So the big structure of today's lecture would be, first we're going to talk about the symmetry in physics and how we can learn that translation and rotation, how it follows the laws of symmetry in physics. And then after that, we will talk about vectors, how these two, translation and rotation, how they relate to vectors, and why we need vectors. After introducing you to vectors, then we will talk about vector algebra, how you can do some calculations with vectors and some of the rules when you're doing calculations. After that, because this is a physics class, so we will talk about Newton's laws in vector notation. And at last, we will talk about the scalar product of vectors. So first, in the symmetry of physics, so how do we define the symmetry in physics? So according to Feynman, he said that one of his colleagues defined symmetry as a thing is symmetry if one can subject it to a certain operation and it appears exactly the same after the operation. For example, if we have two complex machines, and let's say that this is a complex machine. I mean, if we only have one complex machine. So this is a complex machine, and we have two places, A and B. If this complex machine, it works in A, and it gives somehow an outcome in A, and if we move it to B, will it still give this exactly the same outcome? Well, you'll have to think about this because this is not really that easy. If this is a machine and then if you put it in B, what if this is a wall and then you're putting this complex machine inside the wall, and let us assume that there is a ball, or what do you call it, a particle that's bouncing inside this machine, and if you put it over here, it's supposed to come here, but it comes here. It's been bounced off by this wall. So in this scenario, we can't say that if you move this machine to B, they will give the exact same outcome. But how can you get the exact same outcome? How do you adapt it like in a more general form? If we say that in A, everything that is needed to give our outcome is independent of where it is and independent of other forces that is outside this complex machine. For example, if you have a pendulum or a grandfather clock inside it, and on Earth it works quite well, but if you bring it up to space, because there is like a decrease or and there's no gravity, then it won't like spin as it will on Earth. So in this scenario, we say that there is a gravity that is acting on this pendulum, on this grandfather clock. So which means is that this machine isn't self-sustained. There is something else outside of this machine that is not acting on it. But in order to say that a machine or a law has somehow of symmetry, we have to say that everything inside this machine that can lead us to that outcome is independent of anything else, anything outside. So here we say that if we build two exactly same machine, identical machines, and then we displace it laterally, then they should somehow give us the same outcome. So the meaning of this phenomenon is that the same way when we move the apparatus to a new position, so moving that thing, so moving what we think that is relevant to give us that outcome. And if the phenomenon is not the same, if it's something like the grandfather clock, then we say that it doesn't have the symmetry. So in conclusion, if you have to move all the things that is essential to give us that outcome, and not anything else. For example, in this machine, we only need to move what is needed to over here, but we don't need this wall. This wall is irrelevant, so it won't give us the outcome. So with a certain amount of intelligence and a certain amount of experiments, we find that machines like this, they have that symmetry. Okay, going on to the second chapter of this, the second part of this thing, translation. So we recap that in Newton's law, for example, a force, we can decompose it into Fx, Fy, and Fz. And what is it equal to? So for Fx, it is the second derivative of displacement over time. And you have to times it by mass. And Fy, it is somehow the same, but it's just in the y direction. And for z, it is in the z direction. So this is a square. No, it's here, sorry. So this is our equations of the forces. And there exists a way to measure x, y, z in axis. So what it means is that because we say that we decompose it into 3 different axes, which means that we are working with a coordinate that has x, y, and z. But does it mean that if we change a coordinate, will we still get the same value? Or will these laws still continuously be the same? So this is what we're going to talk about. So the relationship with the first part is that a law should have its symmetry if we have everything that is relevant with it. But for example, even if we move this complex machine literally, or if we turn it over a single angle, some angle, it should still work because we're moving everything that is relevant to it. So developing this mathematically, what we can say is that we have 2 axes, and this one. So you have 2 axes. We're only going to talk about the x and y axis. We're going to omit the z axis because it's going to make it a bit too complicated. And we say that this is Joe and this is Mo. And they're measuring something over here. It's a point. They just said that it's a point, okay? And then because they have different origins, like this part and this part, they are measuring in different systems. They're using different coordinate systems. So does these laws still work in their systems? Does it have that symmetry? So this is what we're going to talk about. This is actually something called the Galilean transformation. So if we say that do some labeling, we call this part x prime. We call this part a, and we call the distance from Joe's origin to what we want to measure, we call this x. So some relations that we have right now is x is equal to a plus x prime, and y is equal to y prime, z is also equal to z prime. And so when it comes to the forces, if they want to measure the force on this exact point, we use differential equations to measure the force. Because we somehow have a point over here that's called x prime, y prime, and z prime in Mo's coordinate system. But in Joe's coordinate system, it's different. It is a plus x prime and y. It is x, y, and z. But these are the relationships that we can transform. So this is actually called the Galilean transformation. And if you write it in forces, we should get m times the second derivative of x prime over dt squared, and then you times it by, and then that will equal to x prime. So what this is that in Mo's coordinate system, he measures this force that's relevant to his coordinate system, and he will get these equations. And continuing writing this, it'll give us something like this. We assume that they are measuring all of this in the same time interval, and also due to some measurements they obtain the exactly same mass of this point, which is m. And then what you say is that because dx prime over dt, because we have this relationship, so if we substitute this into here, we will get dx, d over dt times x minus a. And what this will give us is dx, dt minus dA and dt. And due to calculus, we know that if we differentiate a constant against something, we will get 0. So this thing will cancel out. So what we will get is that dx prime over dt is equal to dx over dt. So these two are the same. Even if the coordinate systems are different, there is a distance a, which is a constant that separates their coordinate systems. But if they measure this point and they apply Newton's law to it, they will find that the law, Newton's law, it works in both coordinate systems. Because this shows it. The a, the constant, is cancelled out. So, because we know this, then dx prime, this is like this, and times n is equal to fx prime. And what is this? This is fx. So you say that fx is equal to fx prime. So because we have this result, we say that in conclusion, a machine that is in A and a machine that is in B, and if they are separated, and if we somehow measure what values of what outcomes in that machine in a different coordinate system, the equations that we use are the same, which can be seen from here. And if the equation is the same, then it means that the phenomenon is the same. Because the equations, it comes from the phenomenon. It is just like A to B and B to A. And a proof of the machine that is, so the proof that the machine that is moved from A to B, they have the same outcome, is the proof that they have the same equations. They follow the same equations. So the laws of symmetry for translation and displacement. So this is like the laws of symmetry. We've already talked about the symmetry of the laws of physics inside translation. But just imagine if you are in space, and because you're actually turning yourself constantly. So which means is that there is not only translation, but there's also rotation. And using that grandfather clock thingy, if we say that the grandfather clock, if you tilt it, then it should not work. The pendulum will collide with the walls of the grandfather clock. Which that means is that in that circumstances, the laws of symmetry doesn't work. So if you want to discuss when and how the laws of symmetry will work in rotations, we have to somehow establish a criteria or things, and we will establish it very mathematically. And just like last time, we have two axes. So this will be Joe's axis, and this is x and this is y. And just like the last example, we will take away the z-axis to make things a bit easier. And let's say that this is Mo's axis. It is somehow tilted by an angle of theta. This theta. So this will be x prime, this will be y prime. And let's say that in this two different systems, so in space, we have a point that is over here, and we will call this point P. So if we are like examining it in Joe's axis, the coordinates of P would be x, y. But if we examine this P point in Mo's axis, then it will be x prime and y prime. And so, just like last time, when we were talking about translations, we can use Galilean's translation to establish a relationship between the 2 points, between these axes in different coordinate systems. What it means is that if we know that there is a translation rule according to Galilean translations, we know that in Joe's coordinate system it's x and y, and if we apply that law, that rule of translation, then we will get x prime and y prime, which comes from Joe's coordinate system. So what are the relationships between x prime, y prime, z prime, and x, y, z? So now we will try our best to establish it. So if we draw this perpendicular lines down and separately in these two coordinate systems, we will know that this length right over here, this length is cosine theta. For the math, I'm not going to explain too much. Okay. So this is x times cosine theta, so we will get this length, that is x times cosine theta. And for this length, over here, we will get y times sine theta. Okay? And according to these two, we will get something like x prime is equal to x times cosine theta plus y times sine theta. Because you see, in this coordinate system, the x prime is this part, this length. And in this length, it is x times cosine theta plus y times sine theta. And for y prime, which is this part, so we will need this length. And how do you relate it with the others? Some math tells us that it is y times cosine theta minus x times sine theta, and then for z prime and equal to z because they have the same z axes. Okay, and because our rule and our purpose is to prove that in rotational scenarios, the laws of physics, which is especially F equals to ma, it doesn't change no matter how we rotate our axes. So if there is F equals to ma, we have to examine the forces. So let's say that there is a force. So this force is the force in, this is the force that is in the space. And because it's a force, we can decompose it into the different axes. Into Joe's coordinate system and also in Mo's coordinate system. So which is kind of the same as we're drawing this perpendicular dotted line that we're dropping onto Mo's axis, x prime, and also to x. So what we will get, is that fx prime will equal to m times this over dt squared, and that will equal to, that doesn't equal to anything, and fy prime is equal to m times d prime y prime over dt prime, and over dt squared, and then fz will equal to the same transformation rules as it is. So, is there a symmetrical thing? Okay, let us continue. I found that there is like a flaw in my derivations. So what is missing is that because I've said that the forces, they also follow the same rules as this Galilean transformation. So we know that fx prime is equal to fx times cosine theta plus fy times sine theta, and we also know that fy prime is equal to fy cosine theta and minus fx minus sine theta. And for the z direction, we just know that they're equal because there is no changes in the z direction. So we see that from this equation, we want to know that if it is true in most coordinate system, and we already know that it is true in Joe's coordinate system. So in Joe's coordinate system, we know that we know. So we want to prove that this is correct. How do we prove it? We prove it from the left-hand side and also from the right-hand side. So from the left-hand side, we know that fx it equals to this much. And if we and want to now prove it from the right-hand side, and if in our derivation and our expansion, we find that the expansion of this part it equals to this part, then we can say that these two are equal. These two are identical. I mean, not like mathematically identical, but it means that they are the same. It is true. So if you want to prove it from the right-hand side, so we're going to come over here. So because that this is the second derivative of x prime over time, so and times the mass, and we know that there is a relationship between x prime and the x and y's in Joe's coordinate system. So we will substitute this part into this part. And according to some basic calculus, we will know that it equals to this part. And comparing this fx prime and also this one, we will know that fx, we will know that fx it equals to d prime x, the second derivative of x over dt squared times n. So, times cosine theta, and these two will equal. So what it means is that this one is equal to this one. And so we have already proven that these two are the same. And now what we want to do is to prove it from the y directions, fy. So fy prime is equal to this thing, and then because we have a relationship of y prime with the x and y's in Joe's coordinate system, so we substitute this y prime into this fy prime, the derivative function, and the expansion will give us this thing. And now we compare this part with this part, and we know that fy actually equals to the second derivative of y over t. And times cosine theta, and so we know that these two are the same. So these two are identical. And for the z direction, we know that these two z direction are equal. So all in all, we found that this relationship it is true. It is correct. So what it tells us is that no matter which coordinate system we are trying to measure something that is in space, the laws that we are using is the same. It is consistent. It is what we call the symmetry of physics. So the reason why, the actual data of Fy, the forces of F, the decomposition, the values and the magnitude is different in Mo's and Joe's coordinate system is because that there is a centripetal force that is acting on it because you are rotating it. So in conclusion, if Newton's law works on one axis, then it should also work on the other axis. And if the consequences of these rotations and transformation tells us two things. The first one is that no one can claim that his or hers coordinate system is the only coordinate system that is in space, that is the one that is correct. Because we know that from the laws of symmetry that if we take it from a different coordinate system, we will also get the same laws. But the difference is that you can choose your coordinate system, so the other one might be more convenient than the other. So that is the biggest difference. The second is that any piece of self-contained equipment, they should work when translated or when it is rotated. Well, there is a big significance on self-contained, like what I have been talking before of the grandfather clock. There is an external force that is acting on it. So that grandfather clock is not self-contained. Okay, we're done with this part. Okay, so after you are introduced to the laws of symmetry, and also that the laws of F equals ma, and also all physics law is the same if, according to different coordinate systems, if you rotate the coordinate system or if you translate the coordinate system. So now we will come to what we call vector. So the first thing first, why would we need vector? So the foregoing, you remember last time, when we were deriving the P, the same thing that is in space. And for example, this is a force. And if we measure this force from this coordinate system, and if we rotate it, or if we translate it, so this thing is in space. But if you don't have something called vector, you will have to use a lot of complicated mathematics to do the transformation from one coordinate to the other coordinate. So from now on, we physicists, we have invented something called a vector, which is a powerful mathematical tool that has been devised to address this complicated mathematics translation and transformation thing. And you might ask why vectors will work. It's because of the laws of symmetry. Because that we know that a self-contained machine should work if we translate it or if we rotate it. What it means is that if a force or if something in value it is self-contained, then we know that it should work here, or if we just turn it. So now we have vectors. So there are two types of quantities. The first one is just numbers. It doesn't have a direction, so we just say numbers. The second type it has numbers, but it also has a direction. So we call this a scalar, and we call this a vector. For example, temperature, it is just a number that measures the changes. It doesn't have a direction. You can't say that the temperature is in the north direction. But if we say velocity, if we say displacement, it has a number to measure its magnitude, and it also has a direction. So for example, I am here. So if, for example, my house is over here, and you say that there is a restaurant that is 10 kilometers away from our house. So where is the restaurant? And it should be in this entire circle, this entire area of the circle, because you didn't give me the exact direction. But if you say that this restaurant is of north with me 10 kilometers, then the restaurant should be here. So we have located that point. So this is what we call vector and scalar. And the nature of vectors. So what are the natures of vectors? So first, a vector is 3 numbers. But we will, I will tell you that it is just not it is 3 numbers, but it is not just 3 numbers. So we will first take it as 3 numbers. For example, x, y, and z. For example, a point that is in a point called P in this coordinate system, it has 3 numbers to measure this point: x, y, and z. Yeah, here's the z-axis. And according to the laws of symmetry, and also according to number plus direction, we invent something called a vector. So we call this one R. In textbooks, it's supposed to be in bold, but in handwritten, you put an arrow over here to indicate that it is a vector. So this thing, it represents 3 numbers in a coordinate system. So for example, it represents x, y, z and this point. And so what it means is that it is over here and over here, over here and over somewhere here. So what it means is that you can use x, y, z to locate this vector, but it also has a direction. So let's say that this direction is over here. So we have to go x squares in the x direction, and then you have to go up y squares in the y direction, and for z we'll just say that it's z because we don't want to make it too complicated. So this is a direction that it is indicating. But as we have said, it is but not only these 3 numbers that can change the coordinate systems. Well, what it means is that in this coordinate system, it is x, y, z. But in another coordinate system, for example over here, it will be, this P would be x prime, y prime, and z prime. And as we have known from the translation and also translation and rotation, we know that there must be a relationship between these 2 coordinate systems. So we can use the Lilian transformation to get x, y, z to x prime, y prime, and z prime. But that is too complicated. So what we will need is that we just say that this is an r prime inside space. This thing doesn't change it. This thing is the same in every coordinate system that we measure it in. So this is why vectors are so important in physics. It reduces a whole amount of complications. So talking about forces. So let's say that a force F, it is also a vector, it equals to m times, it doesn't equal to, so it is equal to r prime. And it should be true in any system if it is true in one. So what it means is that if F is equal to if F is equal to r and these 2 are vectors, it is true in this coordinate system, then it should also be true in this coordinate system. So what it wants to say is that this r, which is a vector and it is bold in textbooks, it can represent x, y, and z in one coordinate system, but it can also represent x prime, y prime, and z prime in another coordinate system. And if this goes on, like x prime prime and y prime prime, z prime prime, and on and on and on. So these all, we can use one letter with an arrow on top to represent all these things. So that is why we say that vectors are so important, and this is the advantage of it. Now, we examine some properties of a vector. So after introducing to you all these things about vectors, so let's examine the properties. So for many purposes, conveniently, we represent a vector that is in a coordinate system, which is in geometrically, we use an arrow to represent this r. And this arrow represents, this arrow thingy represents the direction, and we will discuss that the length represents the magnitude and how much it is according to a unit of this thing. But why can a force be represented by a vector? So if we say that this is equal to this, but somebody might ask, why can we use an arrow to represent a force? Well, this is actually the same as mathematically transformation properties of a step in space. So a vector is something like a step in space. Like, this thing is a bit intuitive, but you'll just have to imagine it. It's just it is like a step in space. And a force is also like a step in space. For example, I push this thing. I push it in that direction, and also I have a magnitude that is pushing it. So it is just like a step in space, so you use an arrow to represent it. And a unit force of length. So unit force length, all forces can be represented as length. So what it means is that we say that the length of the force represents how much the magnitude of this force is. And we have like a unit of it to compare. So what it means is like we have F prime and then you times it by K and R prime, and this is what we call the unit force. And all forces can be represented by using this equation because you just need to times it by a constant and then that transforms us to the force that we want. So thinking what is the deeper reason of this? So we can draw lines instead of axes. So now we can draw a line with an arrow, and now we don't need an axis to represent this thing. So it's actually taking away our frame of references and taking away our complicated mathematics transformations. But can we still have x, y, and z? Yes, we can, because we have to observe this force. And when we want to observe this force, we need a frame of reference to observe it. So for example, this is our frame of reference, and we see that this is the force. So in this frame of reference, we can have x, y, and z. But if we if we observe it from here, it is x, y, and z. Then if we observe it from here, then it should be x prime, y prime, and z prime. So it means is that this arrow can represent all. It takes away the coordinate systems in the frame of references. So it makes the problem much more easier. So now we will talk, part 5, we'll talk about vector algebra. So vector algebra, first we will talk about the addition of vectors. The addition of vectors, and we will discuss this in two ways. The first one is the algebraically way, and the other would be the geometrical way. So, for example, if we have ax, ay, and az in a coordinate system, and if we have bx, by, and bz in the same coordinate system, and we measure it. So this should be a in every coordinate system. There should be z, vector, in all coordinate systems. And if we add these together, so you first make a guess. If you add this and this together, what will it equal to? Our guess is that it will be ax plus bx, and ay plus by, and az plus bz. So this is our guess. And if you have a guess, we have an assumption, and now we have to prove that it is true. So, because we're adding these two together, we will first have to doubt that whether this is a vector or not. So, is this a vector? Well, some people will say yes, because it is 3 numbers. But we have said that not all 3 numbers are a vector. A vector, it has to be the same. It has to represent the same thing, no matter how we translate our frame of references and how we rotate our frame of references. And the transformation of frame of references is kind of easy to determine. So now we will determine the rotation of frames of references. So if we rotate, you're going to resolve them on each other, and will they equal? Well, the answer is obviously yes. So how do you prove it? So you remember that thing with Joe and Mo of these two different axes? They have, and this is their turning of the angle of theta. They have that transformation relationship of x prime with x and y, of y prime with x and y. So we will use that same transformation rules into here. So we will observe that if we change, wait a second. So, because this is in one coordinate system, coordinate 1, if you change it to coordinate 2, so this a prime this a vector a, it'll resolve into ax prime, ay prime, and az prime, and the same goes for b's. So, how will this thing change? If this thing changes into ax prime plus bx prime, ay prime plus by prime, and az prime plus bz prime, then it means that the addition of vectors is just by adding the components in the x and y's directions, and also the z direction, of course.
Part 7, we're going to talk about the scalar product of vectors. So what we will talk about is how some of the rules of it and why it is very useful, which is the applications of it in physics. So as you have known that this is a vector, we use an arrow to represent it, and for the notation we use R for this one, and with an arrow on top because this is handwritten. So let's say that this is the vector that we have in one coordinate system, but however, if we turn the thing, what is the difference of the view of this vector, which is in space, onto these two different coordinate systems? Well, you'll know that in this coordinate system, the direction of how the people will notate this vector is different from the direction of the people who is in this coordinate system will notate this vector. So there is like a change. There is like a change in the direction of how people view this. But what is the thing that has not changed is that the length, which is the magnitude of this vector. So this is what we will be talking about. And we use this thing to represent the length of the vector. So from this graph, we assume that the lengths are the same. But are they really the same? Well, we need to prove it. So first, we will write out that R, so we let this thing equals to R, okay? And R, it should equal to, in the first coordinate system, it should equal to x squared plus y squared plus z squared. And the second R, which is R prime, which is in this coordinate system, and this one should equal to x prime squared plus y prime squared plus z prime squared. So in this change of coordinate system, are these two the same? Well, if we use 11.5, which is how x prime relates with x and y, how y prime relates with x and y, how z prime equals to z. So if we use this and then we plug it into, if we use 11.5 if we want to prove that this is the same, then what we will only need to prove is that x squared plus y squared plus z squared, it should equal to x prime squared plus y prime squared plus z prime squared. We will take away this root because it's a bit complicated to calculate. So we just square these two by the two sides. And if we want to prove that these two are the same, so we prove it from the left hand side and then we prove it from the right hand side. And if these two, the way that we prove it from the left hand and the right hand, if they equal, then we say that these two are the same. And if these two are the same, then it means that it is true for two coordinate system that the length of this vector is the same. Then it should be true for all coordinate systems that the length of this vector is the same. So if we do that math calculation, then it should give us this. And I'll omit the mathematical derivations. So now we invent a new thing that is called a scalar function. So what is a scalar function? So we denote that a times a, okay, is that how you write it? Yeah. If we denote that a times a equals to ax squared plus ay squared plus az squared. So this is our definition that we have. So it is also for the same that in the coordinate system there is another vector called b. So b times b, so this thing will represent the scalar product of vector a and vector b. So for vector b, the scalar product of this vector b will be bx squared plus by squared plus bz squared, and we should put this 2 somewhere on top of here. And we can use some of these things. We can use what you have already know to prove that a times b, which we call the scalar product of vector a and b, it should equal to ax times ax bx plus ay by plus az bz. So why is this thing true then? Okay, so first we have to list out all the things that we already know. So what are the things that we already know? We know that vector a times vector a, it should equal to this. We know that vector b times vector b should equal to this. And what we also know is that vector a plus vector b, it should equal to vector c. So if you want to prove this, then we should say we can actually see this vector a times vector a as a c. So if you want to prove that vector a times vector b, the dot product of vector a and vector b should equal to this. So how do we prove it? So these are the things that we already know, and then we will use, which means that we will take the help of vector c, the dot vector of vector c, to help us prove this. So we let vector c is equal to vector a plus vector b, which means that vector c is x, which is ax plus bx, ay plus by, az plus bz. And the dot product of vector c and vector c, which is equal to ax plus bx squared plus ay plus by squared plus az plus bz squared. And if we expand this, which will give us Okay, so if we expand, it should give us this result. And because we want to prove, that because if we want to prove that the dot vector of C is consistent, which means that it's the length of vector C, it is the same. So we will have to write another equal over here. So if this one equals to all of them adding with a prime, which is ax prime plus bx prime squared and blah 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 on, and then if we expand both of them all together, we should get this part, which is the original part, and then equals to the one that has x primes, and with the one that has primes. And we already know that we already know that the dot vector of A is the same in every coordinate system, and also the dot vector of B is also the same in all coordinate systems. So on the both sides of this equation, we can cancel out this part and this part for B, and also we can cancel out the two. So what left us behind is ax prime by prime plus this is x prime, and ay prime by prime plus az prime bz prime. So this is what we will be left with. And now our problem goes on with how do you prove that these two are equal. So it is actually the same as how we have proved that the dot vector of vector A is true. So we use the transformation equations of 11.5 for the left hand side and also for the right hand side. And if the left hand side equals to the right hand side, then we say that this is true. And if this is true, it means that the dot vector of C is true in two coordinate systems. And if the dot vector of C is the same in two coordinate systems, then it means that the dot vector of C is the same in all coordinate systems. So hence we have proved that the dot vector of A and B is equal to ax times bx plus ay times by and az times bz. So this is what we have proved. There is also another property that we have with dot vector, which is the dot vector of A times B plus C. It should equal to the dot vector of A times, you can't say times, remember you can't say times, it is the dot product. So it should equal to the dot product of A and vector A and vector B, the dot product of vector A and vector C. So this is what we should be true. And how to prove it, that thing Feynman said we will leave it to the students as homework. Okay, so this is only the algebraic version of how to prove this. Not prove, how we have invented this. But if we have invented this for the algebras, then we should also invent it for the geometries, the geometrical ones, because we want it to display as a graphics, which is more convenient for us for our analysis. So how does it work? So let's say that we have vector A, vectors over here, and we call this vector A and we call this vector B. So according to what we have learned about the dot vector of vector A and vector B, it equals to ax times bx plus ay times by plus az times bz. Something important to keep in mind is that what at times it doesn't have direction. It is a scalar product. So what it means is that we take the components of A and also B, and then we times it together to form the components of A, B. So how does it work geometrically? So there is a way to do it. So because it is a dot vector, because it is a dot vector, then it should be the same in every single coordinate system. And because we know this, so we can actually turn this coordinate system, which is originally like this, into a coordinate system that is like this, which we will have B. Oh, sorry. Now we will change it to something like this. Yes. Which the vector of B lies on the x-axis, which lies on the x-axis of this new coordinate system. And if it lies on the x-axis of this coordinate system, then we will know that bx will equal to, bx will, well, it'll be the same, and then by, it will equal to 0, and then bz, it will also equal to 0. So this whole part, it will be cancelled out. Sure. And so because that the angle between these two, it is theta. And if you want this come, I can continue. If we want to calculate the dot vector of A and B, we know that if we turn this the original coordinate system of these two vectors, and then we align this vector B with the x-axis, and then we let it put B on it. So now we know that By and Bz is equal to 0. So what left us is Ax times Bx. So what is that? If we want Ax, so what is Ax? Ax is the component. X is the component of vector A on the x-axis. So Ax will be the length of vector A times cosine theta, and then B now times B. So why is it B? Because it is on the x-axis. It doesn't have a decomposed vector on the y and z axis. So the whole length of the vector is actually the length of the x-axis. So all in all, we will know that the dot vector of A and B is equal to AB times cosine theta. So what is the usage of dot vector in physics? An important usage is the kinetic energy. So we know the kinetic energy it equals to a half of mv squared. Okay, and we know that velocity is a vector. But we also know that energy it is a scalar. It doesn't have any directions. We can't say that there is a direction of change of energy. So how about this? We see that there is a vector over here. So how come it becomes like a vector times a vector? So how come this one it produces a scalar? It is because that it can also be written as m times v, the dot product of v. And if it is the dot vector of v, it means that it is the length of the velocity. And if it is the length of the velocity, it should equal to the velocity component in the x direction squared plus the component of the velocity in the y direction squared plus the velocity in the z direction squared, and that should equal to this. So okay, so it equals to this. However, some other things like momentum, it is a vector. So we know that P is equal to m times A. And you see that this acceleration is also a vector. And m is a constant, so constant times a vector is still equals to a vector. So it is not like a square of this, which is, otherwise it will represent the dot product of vector A, which will produce a scalar. So this is the usage in physics. Another very famous usage in physics is the obvious work. We know that work, it isn't a vector, it is only a scalar. You can't say that there is a work in some direction. And you know that the work is equal to the force times the distance of the force. I mean the distance of the force, like, you know what I mean. And these two are vectors. And if I times them together, then that should be the dot vector of force and the distance traveled. So what it will give us is fx times sx plus fy times sy plus fz times sz. So that is what it will give us. So mathematicians and physicists, they found out, or you can say they invented this scale product, which is something that doesn't change in all coordinate systems. So if something that doesn't change in all coordinate systems, we can actually invent a new way of representing things, which is way more convenient of the others. So let's say that we have a coordinate system, some coordinate system, some regular coordinate system, and we say that it is like this. So what they invented is called a unit vector. What it means is that there is a unit vector I in this x direction, and then there is a unit vector of j, yes, j in the y direction, and then there is a unit vector of what do you call it? K, yeah, k in the z direction. And because that we know in every single corner system the length of I, k, and j, it is the same. So what we all know is that I squared, which is I times I, and these two are vectors, it should equal to 1. We let it equal to 1. This is why it's called a unit vector. We defined this bit. And also, k times k, it should also equal to 1. And it also goes the same for j times j, and that should also equal to 1. But if we cross times, which means I times k, I times j, j times k, and blah blah blah, it should be equal to 0. Why? Because we know, okay, for example, j times k, we know that it should equal to cosine theta. And what is the degrees of j and k? Well, it is 90 degrees. So cosine 90 degrees. And cosine 90 degrees, it should equal to 0 of j times k. So it should equal to 0. So that is the reason why if you times these two, it should equal to 0. And if we know this, we can actually represent a vector that is, you can invent a representation of a vector that is consistent, that is the same in every single coordinate system. So for example, if we have a vector called A, and then we let it equal to AX times this unit vector of I, and then plus AY times this unit vector of J, and then AZ, we times this unit vector of K. So we let AX, AY, and AZ, we let it be some constants. And as we know, that a vector, if you want to add up a vector, for example, if you say these are the two vectors in the three directions, and you want to add them up. So head to tails. So this is the first one, and then if you want to add these together, well, you can't add them together anyway, so it should equal to something very, very small like this. So as you know, that this is actually the additions of vectors. And in the additions of vectors, it should actually represent a point in a coordinate system that has x, y, z from the from the origin. And the reason why we use a unit vector is that a unit vector, it's because that if we use the normal way to represent vectors, it will change in different coordinate systems. But we don't like that. We want them to be the same. And if we want them to be the same, we know that so if we want to be the same, we invent something called a unit vector. And we define that the dot product of I, k, j equals to 1. So the 1 is like a unit. And then we use ax, ay, az as constants. And then we times it by those vectors, which would also produce a vector. And then we add those vectors in the 3 directions together up, and that should give us a vector in space. So this is how it is done. So a summary of this long and lengthy class, the entire one, is that first we know that a very complex machine, if we move everything that is relevant with it to another place, and also the movement can be rotation and it can also be translation. It should produce the same output if we move everything relevant. So now, if we know this, then we can somehow say, or we can somehow doubt that the laws are the same because the phenomenons are the same. And if you know, because from experiments we know that the laws are the same, so now we wanted to prove it in mathematics way to see that if our math is correct. So first we prove it from the translations, and then we prove it from the rotations. And then when you have proved these two, then we say that wow, the laws of Newton's, the laws are the same in different coordinate systems. Well, there is like a special case of special relativity, which we will learn later. And then we invent something called vectors. The reason why we invent something called vectors is because that if there isn't a vector, when we want to change our coordinate system, which for convenience, there will be too much of complicated mathematics. But if you invent a vector is a quantity that has both magnitude and direction, and a scalar is a quantity that only has a magnitude. And a vector, it should be the same a vector should be the same in every single thing. The vector should be the same. It should represent the same thing. Okay, it should represent the same thing in different coordinate systems. And then I introduced you to the calculation rules of addition, subtraction, timesing it by a constant a, and also the time derivative of a vector. So these all produces a vector. And after that, we talked about Newton's law in vector form. And I also proved it to you why that is true by first proving that acceleration is a vector. And some students, they think that vectors are still useless. So I demonstrated you with an example of how we can use vectors and why it is so important, which is the one that you all know, centripetal forces, that example. And after that, we found that there is one thing that doesn't change in every single coordinate system of a vector, which is the length of the vector, which we'll call the modulus of the vector. Because it doesn't change, so we invent something called the dot product. So the dot product of vector A is notated as A of vector A dot of vector A equals to blah 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 blah. And then I also introduced you to the dot products of A and B, both in algebraic and also in geometrical ways. After that, we have introduced, after that we already know what a dot product is, something that doesn't change in all coordinate systems, no matter how we rotate it, no matter how we translate it. And if we know this, then you want to develop a new notation system that is more convenient, that is more consistent. So we invented this. And this whole entire class is how we know this. Thank you.